Section 1.5 Sets of points in the complex plane. Definition. Suppose x0 equal to x0. Suppose z0 equal to x0 plus I y0, since the absolute value, the modulus z minus z0 is equal to, as defined as this square root right here. Then the distance between the points z equal to x plus iy and z0 equal to x0 plus I y0, will satisfy this equation, right? It is the points that satisfy this equation, right? The points, right? Sorry, I can't read my handwriting. So this is the equation, right? Rho is greater than 0, then it lies on a circle of radius rho, right? A circle radius rho, right? Centered at point z, right? So now let's do an example. Let's say the modulus of 1, right, and is an equation of a unit circle centered at the origin. You can view it as, well, really just, you can think of it as 0 minus z minus 0, right? So that is equal to z square, right? That is equal to z. So that is, so now this is not really the z. This is not just x. This is not just 0 plus 0 I, right? Sorry, this is not. Actually, z is equal to our rho. You can think of it like that, right? So we can really draw it. I don't think they have it on the textbook, but I'll just draw it for you. It is really just this, right? Center at 0 with z. Let's say z is over here, x, y, right? Then it forms a circle, right? So this is that, right? So now we can really just write. We can just really annotate this. We draw over here, right? We have let's neglect the axis, right? We have z0. So this is general case when you have radius rho, right? And it forms this circle. And what does this mean? Well, written in our definition is really just z minus z0 equal to rho, right? So what is z? Well, z is on the axis, no, on the edges, because, well, this is equal to rho, right? So equal to rho, well, this is, let's say, call this z1, right? This is z1, or x1, y1, right? And this is, let's call it z2. Both of them satisfies this equation, this inequality, right? Okay. And let's do part B. Rewrite, let's say, well, let's say z0 is equal to -1 plus 3i, right? Okay. Well, then it really becomes this, right? Plus 3i. Oh no, it's minus. Sorry. Then this is plus. This is minus, right? And, well, minus what? Minus 5i, and that's 3i, right? Sorry. Minus 1 plus 3i, right? So this is minus. This is plus. Well, they want the they want the radius to be 5. Well, now we want to draw it, right? So z minus, how about we factor out negative sign, right? Which is exactly our z0, right? And now we want to draw it. Well, you have axis. How about we draw over here, right? We have 1, we have 3 over here, and this is, well, really just 3 minus root 5, right? well, I'm sure you can simplify, but this is how much already. Okay, so now you want to draw a circle, right? So that this corresponds with this inequality minus 1 minus 3i there is equal to 5. Okay. So now the points z that satisfy the inequality modulus of z minus z naught less than or equal to rho can either be on the, which can be either on the circle of this inequality or within the circle, right? Because it's less than or equal to, so it can be on the edges or it can be off the edges, which is in it, where we say that the set of points defined by this inequality modulus of z minus z naught less than rho is a disk of radius rho centered at z naught, which is illustrated over here. I drew the image, right? And well, you have center at z naught, and this is radius rho, right? Rho. And now definition: the points satisfy strictly modulus of z minus z naught less than rho lies within, not on, this circle of radius rho center at z naught is called the neighborhood of z naught, right? It means it's not included the boundaries, right? It's really just defined by this inequality, right? Excuse me. Definition: if the set of points that satisfy the inequality 0 less than modulus of z minus z naught less than rho, that is z naught is excluded, right? Which is, well, radius of 0, that is z naught, is excluded. This set is called the deleted neighborhood of z naught. Now another definition: a point z naught is said, a point z naught is said to be an interior point of the set S of the complex plane if there exists some neighborhood of z naught that lies within S if every point z element of S is an interior point, then S is said to be an open set. Well, that is, well, if we look over here, right? So this is this is z, right? And then we want to look at the boundaries, this one, right? And if we zoom in, we construct this neighborhood, and no matter how small we construct it, we can never reach the edges, right? And the edges does not include an element, what does not count as an element of z. So the edge is not an element of z, right? So this is an open set, right? So we say this is to be open, or S is open, right? And if we go over here, if we construct a neighborhood over here, right, and we see some of the points, if you would observe closely, some of the points are not S and some of the points are within S or element of S, then this is said to be closed, right? Or you may just, well, we haven't learned it yet, so this is not open. S is not open, right? And now let's do some examples. Now, if you have, this is your y-axis and you have your x-axis, but how about we do not include our x-axis? We define everything under the x-axis, right? Well, how do we come up with a function? What is this? No, how do we come up with an inequality? Well, that is the imaginary part of z, well, that is the y-axis, is in fact less than 0, right? So this defines S, right? well, let's do it with a more mathematical way that the textbook didn't write it in. So how about we define S as all of the points such that the imaginary part of Z is less than 0. So this is how you write it more mathematically. And now we observe part B, that is this figure, right? The edges are not defined, well, are not included, right? So only the colored parts are element of Z, so this is Z, no, S, so this is S, right? So this can be defined as, well, -1, we want excluded, so we want the real part, right? So this is X, this is Y, and we want the real part of Z is less than or equal, well, is between -1 and 1, right? And this is, and in fact, let's give it a name. So we call A a lower, we call this a lower half plane, right? And we call this an infinite vertical strip, right? And now I think I'll run out of space. Well, this, now we have axis, right? Sorry. And if we would draw a circle in, right, and then we define everything besides a circle. Sorry, maybe there. Right, and we say this is such that the modulus is greater than 1, right? And what is this? This is the exterior of a unit circle, right? That is, it is not in the circle. I think it's quite clear, the language. And now, well, let's take a look at this one. Space. We have a circle, and you have a circle over there, right? So I think in calculus you call it a washer, right? This is a washer. But in complex analysis, right, we call it the interior of a circular ring, right? And, well, we can define it as, really, like that. That's between 1 and 2, right, the modulus. There. And then now, definition. If every neighborhood of a point Z0 of a set S contains at least one point of S, then Z0 is said to be a boundary point. Well, if we look over here on the left, right, this over here, now, what does it mean to contain, at least one point? Well, if we go over here, we draw we draw a neighborhood so small like that, right? Although most of them contain an exterior point, but notice that on some point over here we still contain the interior point, right? So that is the smallest neighborhood we can get. So that is called the boundary point. Well, this is very real analysis. So real analysis, they choose a point so very small, and then it contains a little part of S, and then yeah, so that is the smallest set. But now we're in complex analysis. It doesn't have to be small set. But that's what it is. Now, a collection of boundary points of a set S is called the boundary of S, right? So if we look over here, if we collect, in the more common mathematical parlance is that we call it, we add all of these boundary points, and well, that is the collection, and then that is a boundary of S, right? And then so you write it as like union. But a point that is neither an interior point or a boundary point is called an exterior point, right? So over here it is not interior, it is not a boundary point, so that is an exterior point, right? And where am I? So, well, for example, if we let's say if we define a circle like this, right, minus I, that is equal to 2, right? Now maybe this, right? I am inventing an example. Well, that's all. That's something I do, right? And well, let's say, well, so this can be drawn as this, and you have your y, you have your x, you have your I, right? This is I. Well, that is really just the imaginary part. So now, if you want to draw a circle, well, that is 1. Well, how about, well, then it's over here, root 2i, right? Negative root 2i, and then you have root 2i. Really, that's just radius, and then you draw the circle, right? And then, come on, right? So you draw the circle, and then since it's less than or equal to 2, well, that makes our boundaries inclusive, so it is solid lines like this, right? And then we define everything in it, right? And now, if you want to ask, what is the boundary? Well, the boundary, this is the boundary, let's call it boundary. It is a set of xy, a set of points, such that maybe z minus I is equal to 2, so that is how the boundary is defined. And if you want to find the interior of, we want to find a definition that defines the interior of the circle. Well, that is a set of points xy such that z minus I is less than 2. So, right, and then we say S is basically just B union I, right? So that is what this inequality defines. So we call it S, right? Really. So that is that. And now, for a value rho 1 such that rho 1 is less than the modulus of z minus z naught, and a value rho 2 such that rho 2 is greater than the modulus, right? Then an open circular annulus is, or annulus, I think. A circular annulus, I think that's how you pronounce it. Circular annulus, is defined by the inequality such that rho 1 is less than the modulus and is less than rho 2, right? Now, and let's write an example. Let's see. So, well, let's start with let's do a more abstract example. So, what is? Well, let's write the general annulus region. Well, you should see this, because let's say your rho can be, since your rho is the radius. Well, it can be it can really just be defined as a function of theta, right? And so is your rho 2, really. So this is more abstract. And well, then your region, let's say your circular annulus region, is just RCA, right? Well, then let's say it is defined by this, right? This is ugly. Maybe this, right? So this is your rho 2, really, this, and then now you have something like this. Maybe like this. That looks so ugly. Maybe no, it looks like intestines now. Maybe like this, right? So this is your row 1, right? So this is your RAC is this part, right? So this is your RAC. No, RCA. Sorry, there, right? And that is example 4. Now let's move on. If any point of, if any pair, I think it's any pair, if any pair of points z1, z2 in a set S can be connected by a polygonal line that consists of finite number of line segments joined from end to end. I think this should be from end to end. That lies entirely in the set, then the set S is said to be connected. Well, an open connected set is called a domain. Let's come up with a picture of a domain, right? Openly connected, eh? Well, how about we do this? We draw. Let's call this Z1, right? This point Z1, and let's say this is Z2, right? And if you can join, and if the set is, its set is like this, really weird set, right? And if we can join with finite line segments like this, then S is connected, right? And if we join all these open set together, right? Open connected set is called domain. Well, that is really just. Well, let's do another example, right? So if we have this is an open set, right? And you have Z1 and you have Z2, right? And they are joined. Well, they certainly are connected, right? And they are open, and that implies, S is, that implies it is the domain, right? Domain of S, right? Something like that, right? And now, a region is a set of points in the complex plane with all, some, or none of its boundary points. An open set does not contain any of its boundary points. It is a region. Well, that is the corollary. And now, a region that contains all its boundary points is said to be closed, right? And a closed disk is defined by the inequality. The modulus z minus z naught is less than or equal to rho, and the modulus z minus z naught is less than rho defines an open disk, and a punctured disk is defined by the inequality. 0 is less than the modulus and is less than rho, or it is inclusive, right? It's less than or equal to rho. So now, another definition. What is this? And sorry, I can't read this. Yes, an annulus or annular region, right? An annular region is defined as a region that is hollow in the middle. That is, the region encloses a region of lacuna. So, what is an annulus region? I think we did an example over here, right? So maybe like this, right? And this is an annular region. Or, well, I mean, oh, this is so ugly, sorry, I can't bear this. Now, better, like that, there, and well, let's draw something peculiar, something like this, right, and I think this also qualify as an annular region, a generalized annular region, right? Well, let's take a look at a closed disk. What is a closed disk? Well, we have around z naught, right? And we include our boundary, right? And then this says yes, so this is a disk, and it includes its boundaries. So this is a closed disk and a punctuated disk. Let's just do this one, right? It is not inclusive, so it is an open set. This is called an open punctured disk. Alright, and then you have, note that this is not inclusive, right? Okay, because it is a hollow dot. So now this is an open punctured disk, right? And now a set S in the complex plane is bounded if there exists a real number r greater than 0 such that the modulus of z is less than r for every z neighborhood of the origin. So that is, well, if you write it mathematically, it is S is equal to a complex number z is equal to the point z, well, x and y, right? And such that r is greater than 0 and r is greater than the modulus, then S is bounded. A set that is not bounded is said to be unbounded, right? So there, I forgot to underline it. And now I forgot what I'm doing. What is example 7? A set that is bounded. Well, let's do an example. I think maybe something like this. Well, let's do a disk around z naught, right? Something abstract, not just numbers, just z naught in general case. And well, let's make it solid, right? That is a closed disk, right? About z, right? And well, it certainly has this radius rho, right? And well, if we let r greater than rho, right? But because we know that this is z naught, right? And it is less than or equal to rho. So if we take the maximum value of this inequality, right, of this set, right, that is equal to the points such that rho is maximized, right? Maximize rho. Well, that is the modulus is equal to rho, right? And so if we choose r is greater than rho, then r is greater than the maximum value, right? So that implies our r is actually over here, right? Let's say our r, right? So, and now we can construct this circle over here or something, all right? And since r is greater than rho, and that implies r is greater than this number, right? And since rho is, it has to be a real number. It has to be a real number. And we know that in real analysis, the real number system it is, well, it is complete, or it's unbounded, right? Sorry, we're not talking about the completeness over here. We're talking about it is unbounded, right? So because you can always find a real number that's greater than the previous real number, right? So let's say r is greater than rho, then it means that r is an element of real number, and such r exists, and there exists a rho. No, there exists an r such that r is greater than rho. So therefore S is bounded, right? By the definition, S is bounded if such R exists, right? And now we want to find something that is unbounded, right? Let's do an example that is unbounded. Well, we don't really have to just define a disk, you know. We can, it says a set, right? A set is inequality such that points falls in some definition, right? So how about we define it as this, right? We have y and x, right? Just for a bit, well, I think we did this one already. Let's do this one, right? This is called a vertical stripped, right? And you can find, let's say you want to find an r, right? You want to find an r. R is greater than sorry. Let's look for it. What is it? A real part. So let's start with this. S is equal to all the points such that it is the real part of z. It's bounded between -1 and 1, right? And let's say we found an r that is greater than scheiße. no, I should erase the r. No. Oh, this will work. Alright, so this is your set, and if you well, there exists some r that is greater than this, right? Greater than -1. Yes. R is greater than -1. You can choose r, right? So choose r such that, or let's say choose r equals to, like 2.5 was over here, right? It is greater than, it is out of it, yes, but note that r is not greater than rho, because really if you want to find rho or what is the definition, it is greater than the modulus, right? But the modulus really it is infinity, right? Because, well, this is not a circle really. You can, like, come on, you can always go down like infinitely, and there's no r that is greater than infinity, because you can't really compare infinity. So this is actually unbounded, right? Unbounded. S unbounded, right? So this is an example. Definition: the notation for increasing without bound, and decreasing without bound is denoted by x approaches positive infinity and x minus approaches negative infinity respectively. Sorry, I can't read my handwriting. It turns out that we can get along just fine without the designation, well, plus or minus infinity, all right, by dealing with an ideal point called the point at infinity. So an ideal point is just, well, it is point at infinity, so these are called ideal points, because when conditions are ideal you can approach infinity. So this is an ideal point, right? This approaches infinity, right? And another definition: the set of real number r adjoint with infinity is called the extended real number system, right? And now let's move on to the last definition, really. Definition. In complex analysis, only the notation of infinity is used because we can extend the complex system C in the manner analogous to the way of R, right? And however, we what do? We associate a complex number with a point on a unit sphere called the Riemann sphere, right? This is the Riemann sphere, really. So this is North Pole, right? If we 0, 0, 1, so let z equal to a plus ib's, and then we write in this coordinate system ab 0, right? And such that this sphere is defined as x squared y squared plus u squared is equal to 1. Really, it's just then this is the u-axis, really. Yes, and then this is the complex plane, right? And this is the complex plane. If we define this dot as any complex number, and when it approaches infinity or anything, it really doesn't matter. Well, just any complex number on this complex plane, and if you draw this triangle, right? Well, this is AB0, then this has to be x0, y0, and u0, and you don't know what they are. Okay? You don't know what they are. And there's always this point, there's always this point on this surface. You can think of like that, right? Because really when what is wrong with this iPad? Right? If this is infinitely large, right, it's over here, you have a unit sphere, right? It's like over here. It's just sticking up. So if you draw a triangle like that, you will see that this point will approach the North Pole, right? Well, now the system the system consisting C adjoined with the ideal point infinity is called the extended complex number system. The way of mapping the complex number onto a sphere, or North Pole 0, 0, 1, that is what is excluded. It is called a stereographic projection, really, because you can really never touch this point with your point on a sphere, right? And that is section 1.5.